Thank you very much. Good afternoon, everybody. I'm going to open this session on description logics, indeed by presenting my contribution together with Franz Baader, who cannot be here, on expressive power of description logics, which are concept languages. I will go into that in a moment, with a particular focus on quantitative extensions that can deal with numbers and with some also semantic restrictions. So since we will hear 3 talks on description logics, it will be good to give a one-on-one. Description logics are, in a nutshell, knowledge of representation languages that are rooted in logics, clear semantics, clear syntax, and clear decision problems. If we look at the pipeline of how description logics are studied and applied in practice, we can locate 4 stages: the domain knowledge, expert knowledge, that's usually from the human domain, or let's say human experts, or also machine-derived knowledge that we want to formalize in a structured format, such as an ontology, that we can then feed to a reasoner, which ideally, depending on the language that we have at hand, is able to perform automated reasoning, give us a decision that then will be fed back at different stages of the pipeline, either to correct our ontology, updating it, to act upon domain knowledge, or to inform the user. And we will see also in later talks different focuses on this pipeline. Here we will focus mostly on what motivates the design of a certain description logic or language by talking about their expressive power, which we will also define formally and study using the methods of formal languages and model theory. Right. And while these are theoretical languages, in a sense, they are also used in practice. Most notably, description logics have been used to design and formalize the web ontology language. And this is a web semantic web standard, sorry. And it's been used, for instance, to author ontologies in the biomedical domain. Right, let's go through some basics, which I will then remap to notions of first-order logic or modal logics. So we start with some building blocks, which we call concept names and role names. Concept names are essentially unary predicates. They describe properties of a certain individuals, and they are used to collect categories of individuals, whereas roles are binary relations, and they are used to relate two individuals according to some relation. These names are used to form concept descriptions. These are in your modal logic or first order logic parlor, these are formulae with quantitative variable or modal formulae. What we also call particular description logic is dependent on what constructors will allow. So for instance, ALC is allowing for negation, conjunction, and some restriction on the roles. This is basically a model diamond, if you're familiar with that. And we can use indeed these constructors to build descriptions, but also to build rules that then will constitute our ontologies. So for instance, in this example, we talk about the fact that every human that has a child should be eligible for a tax break. You can read this inclusion as an implication, indeed. And you can imagine this graphic representation on the left as a way to kind of solidify the intuition about what the names are used for, but also how the semantics is given to this formula with classic cryptic structures or interpretations. And of course, then we have decision problems that connect syntax and semantics. And for instance, one of them can be the consistency problem for ontology, namely, given a set of inclusions, check if there is a model that satisfies all of them. And we know that for ALC, which is a rather standard language, this problem is already exponential time complete. If you, on the other hand, will only focus on a concept language, as we will do later, and just ask, is there a word or an individual in an interpretation that satisfies this concept? This is p-space. And for those of you that are familiar with modal logic, ALC is multimodal case. Right. We have two particular ways in which we integrate quantitative knowledge in description logics in let's say, the well-established ways. The first one is through counting of cardinality constraints, where now we not only specify whether there is a relation or there is not, but also specify an amount. So if we want to refine our rule about eligibility for tax break, we may want to say humans that have 3 children are now eligible for a tax break. And indeed, just to exemplify that now we have an ability to count relations that before was not there. And that in spite of this increase of expressive power, we are still able to do reasoning in exponential time, which is nice. It's so robust in a sense, maybe not the fastest, but it gives us guarantees about the inner workings of these logics. And so we have one way constituted by counting over relations, and another way which we call concrete domains, where the idea is that we fix a relational structure or just a fixed set with fixed relations that we can use to talk about specific attributes of individuals. Typical examples are salary, age, some forms of scores. So some real numerical data that's not just dependent on the relations on the first order side, but really comes from a different source. And we interface the logic with these values through feature names. It's essentially an additional element of the signature that allows you to assign to a specific individual a value. And for instance, here we have two rules. The second one essentially says that a mother is someone that has a child whose age is smaller. Or on the top side, we verify even more our criteria for tax break eligibility. And we want to say that the salary has to be smaller than 100,000 of your favorite currency. Right. In the semantics, we imagine that now we have an additional element. The fixed concrete domain is here depicted in red, or just the vertical arrow, if you will. And indeed, these feature names are assigned to partial functions. So not every element must have values. If they do, they may have to satisfy some constraints. And yeah, based on that, we define our decision problems as usual. And here in particular, the choice of what you use as a concrete domain may influence the setability. Here we have two decidable cases, the rational numbers with ordering or rational numbers with so-called unary predicates. We just talk about one value at a time. There are other instances that are decidable with numbers. So for instance, integers with comparison. But there are also undecidable cases, like the naturals with the successful relation. And you will see in the later talks of this session, there will be other concrete domains treated for some particular properties, for instance, equations over the rational number. These are the two ways in which we introduce quantitative reasoning in description logics. And when we want to study the impact they have on the expressivity of a language, we need to somewhat be formal. We deciding what we mean by expressive power and then conduct our studies. In this case, we focus on the notion of equivalence. Here you have the same concept of formula expressed in 3 different ways in 3 different languages. So on the left, you have ASC, in the middle, ASCQ, on the right, first order logic. And by equivalence, I mean that this formula will have the same class of models, right? An individual in particular is a model of the formula in first order logic, if and only it is represented by this concept description. And this is ranging over all interpretations. They can be arbitrary. And yeah, we may want to restrict this, as we will do later, for a host of reasons. But for instance, if we are learning concepts or if we are treating concepts that are somewhat derived from real world cases, all the interpretations we have are finite. So maybe we want to really talk about equivalence module of finite interpretations and all of them. Yeah, we will call first order declinable of the concept that has an equivalent first order formula. Equivalence, I describe what it is. And we use some visual representation, like if you just need a visual reminder of what we're talking about. Equivalence is going to be a box with two elements in the same box. An arrow that goes upwards means that these languages can be separated. One is more expressive than the other. Something that has a blue border is first order definable. And it's important here to remember, we are assuming that we use always the same signature. We do not introduce more names. This leads to alternative versions of expressive power. Here we're just assuming, okay, if we have relations on the description logics, concept of all names, then in the first order formula, we can only use those as unary and binary predicates. Right. One tool that we use in description logics, but also model logics, and also in other areas of first order logic, to characterize expressivity or study non-expressivity is known as bisimulation. And the most basic version of bisimulation is the one for basic model logic, or in our case for ASC. So it's a binary relation between interpretations that satisfies certain conditions, namely the atomic condition. Two individuals that are related must be satisfying the same concept names, so the same unary predicates, and the back and forth conditions. So if two individuals are related, one of them has a connection with a certain individual, then on the other side, we must be able to proceed likewise, and in such a way that the two targets are also bisimilar. This is what the back and forth condition says in a nutshell. And a very famous result, one of the main results of logic, if you will, is what is known as the Van Pensen theorem for ASC or also for basic model logic. So a first order formula is invariant under bisimulation, namely its satisfaction is preserved among individuals that are bisimilar, even only this is equivalent to some ASC concept or basic model formula. Van Pensen did this with respect to arbitrary interpretations. Later, generalization by Rosen gave us a way to prove this also in restriction, for instance, to finite interpretations or finitely branching ones, namely finite out degree. So trees where you have at every level of depth only finitely many branches. And in fact, these two proofs are quite different. They rely on different properties of first order logic, and some of these properties may not hold in some of our settings. For instance, when we have concrete domains, we have a new kind of logic that is this compact, is this localizable, do we know, don't we know, we need to prove this, so we may want to use one or the other. Right. And with this bisimulation, we can, for instance, also show non-expressivity. So here you can see that an individual to the left has only one child, the individual to the right has three of them. This means that we cannot, within our language ASC, create a concept that can distinguish these things. Therefore, we cannot express upper bounds, for instance. We cannot say there is at most one child. This is only pertaining to ASC, which is thus more expressive. Right. I will now present the main results of this paper. I'm going to give an high-level overview. On the first part, let's say, I will focus on cardinality constraints, so counting of relations, and I will introduce a slight generalization of ARCQ, where we are allowed to do more with counting, and present our results there. On the second part, I will talk about logics for concrete domains, and in particular, to kind of create an analogous of Van Pensen theorem, I will also have to talk about first order logic with concrete domains and explain briefly what that is. Right. So we study the expressive power of cardinality constraints for a logic that's slightly more expressive than just having counting with respect to fixed natural numbers, which we call ASCST. And in this logic, we cannot not only use this sort of lower and upper bounds, but also compare cardinalities of sets that are in a certain relation. So, for instance, this formula says that this particular individual must have as many pets that are dogs as children Okay. And in particular, this is an example that's satisfied by my parents. They have 3 dogs, they have 3 children. They're fine. They pass the test here, right? This logic is indeed more expressive than what we had before, and is based over a theory that may be known to people doing satisfiability modulus theory. These are setting cardinality constraints over finite sets in their original incarnation. This is going to be an NP-complete theory. And what we did initially was to extend it to infinite sets. Why did we do that? And why did we care that it could use infinite sets? Because indeed, traditionally, description logics only they are not restricted to finite interpretations, but they evaluated over arbitrary interpretations. So if we want to have a fair comparison of the expressive power of languages, we need at least to have them agree on the semantics before we do a comparison. And this is indeed then what we used previously. We said, okay, we compare these logics over all interpretations. And in particular, we show that this is using results that they execute. So the counting we did before is less expressive than the counting that we can do here. But we also did something more. We introduced a notion of bisimulation that can properly capture the expressive power of this fragment. And in particular, here the back and forth conditions are a bit more expressive. We do have more refined control over how we reach from one individual to the other. So we talk about the safe role types. This tells us exactly what kind of relationships, in what kind of relations two individuals are. And then we not only do the back and forth step controlling one individual at a time, but we go over sets, finite sets, and we make sure that if we have a finite set on the right-hand side that can do certain things, then on the left-hand side there must be a set with as many elements, and so that we can also establish a bijection and have bisimilarity there. If you are familiar with gradient model logic, there is a similar bisimulation, but instead of using these safe role types, it only uses rows or modalities. Right. We have our Van Benton results here. First, we showed it for all interpretations, as mentioned before, but here we actually are able to generalize this to also talk about finite and finitely branching interpretations, and therefore have a more complete picture. But not only that, this also gives us a particular idea of what formulae in these description logics can be expressed in first-order logic, and so they enjoy the nice properties of first-order logic. And these are essentially, again, only comparing with respect to fixed natural number. And this is, in a sense, giving us quite a clear idea of what makes also this language more expressible than first-order logic. And in the paper, we go a bit more fine-grained. There are a number of technical results hidden in there that we use to separate the first-order definable fragment from the other one, and similarly how we can indeed obtain this result characterization over restricted classes of models. Now, for concrete domains, as mentioned before, we do need to introduce a more general framework to enable a comparison, and we do this with first-order logic. And here in particular, we more or less in a similar vein introduce 2 classes of additional base predicates that allow us to talk about feature names. So we have definiteness predicates. They tell us a given individual must have a value or not. And then, let's say, concrete domain predicates. These tell us how we relate the values of these individuals. And here, just to spare you from parsing the formulae, I added the natural language description. The first one will give us a way to define an objective function over a specific feature. And the second one instead would allow us, for instance, to specify triangles of values that are smaller, which of course is unsatisfiable if we take the rational numbers with ordering, for instance. Right. Now, to be able to formulate our results, we do need some particular condition that's not necessarily satisfied by all structures, but simply said, we just need to be able to negate a constraint and obtain more positive constraints. Otherwise, it's harder to encode some of our nice properties. And this in particular is a notion which we call weakly closure or closed under negation. If we negate a predicate, we obtain a choice between several predicates. And this is a very natural property of rational numbers. Two numbers are different if one is smaller than the other. So we can choose which of which, but it's always there. Here we also introduce a bisimulation. Now we have to, of course, not only have conditions on the first order part, if you will, but we also need a condition on the concrete part, on the features and how to restrain them. And these conditions it says that if on the left-hand side we have some values that are in a particular relation, we can find them on the right-hand side. This time, we don't really need to do a full back and forth. We don't need to add additional conditions on the bisimilarity. It's just talking about the values. They just have to exist or not to satisfy some specific constraints. Right. Again, we can use these to prove expressivity and non-expressivity results. What's interesting here is that given that we have choices for concrete domains, we can also use this notion to separate logics that have the same base first order logics, but different concrete domains. So for instance, if we take successor relation and a double successor relation, we show that one cannot really simulate the other, at least with such a base logic as ASCQ. Or for instance, if we only allow for simple restrictions that talk about one constraint at a time, we cannot express, for instance, the uniqueness predicate. We cannot express that there are three values such that one is between the other, which may be a useful tool for non-expressivity, but in this case was to showcase how this notion can be used in the negative as well. And in the positive, we are not doing one-method characterization. This time we respect not to first order logic, but first order logic with concrete domains. And it required again some technical results, especially to the properties that we were not sure that first order logic with concrete domains would satisfy. So we had to do some additional work. Right. Picture of the summary of the paper. We have basically a study of characterizations of logics. We did introduce some simulations. Here in the middle, it's what's not shown in the slides, but in the paper, which is the technical work, of course. And on the right-hand side, you will see then what expressivity hierarchy we obtain. And as for future work, we may want to study more logics with numerical constraints. Here we just focus, for instance, on concepts of formulae that talk about an individual, but we may have rules that are numerical in flavor, such as saying the number of individuals that satisfy a certain predicate in the whole of my interpretations is greater than those that do not. And we have some previous work, but this is not generalized to restricted classes of models. We may want to study the expressive power when we combine these two formalisms, and we did the first work of studying the complexity of reasoning in this combination in our code paper accepted this year. Or we may want to investigate different notions of expressive power, for instance, conservative extensions where we are allowed to add more symbols, which is quite natural. Of course, in practice, if we want to simulate the behavior of a system, we may want to use additional auxiliary symbols. Thank you for listening.